In this short video, I'm going to show you how to create simple SQL queries using the SqExpress library. As a test database, we will use the well-known Northwind database, which includes categories, employees, and so on. Let's create a simple query that selects records from, for example, the categories table and verifies the existence of data. Now it's time to create a demo.NET 6 console application, which will demonstrate some basic features of the SqExpress library. We will simply call it Northwind. Finally, here we can see some SqEfolded code, which we do not need, so simply removing everything. The first step after creating a new project is to reference the library from NuGet. We find it by its name, and by clicking the Install button, we create the reference. The library is installed, and now we are ready to create our first query. To do this, we type the class name SqQueryBuilder and specify the required static method, which in our case is select. However, currently there is nothing to select because we have not created table metadata. To generate it, we can use the built-in tool, which is called GenTables. The first argument is a database type, the second is a connection string to our database. After the tool execution is complete, we are able to see C# classes that describe the database tables, and inside each table descriptor, we can see descriptors for its columns with their own metadata. When we have the descriptor classes, we can use their instances to address database tables and table columns in queries. Let's create an instance of a descriptor class that represents the categories table using the static class allTables, which contains instance factories for all database tables. The properties represent corresponding columns, so let's list them as arguments of the select method: category ID, name, and category description. The from part of the query should reference the table descriptor instance we've just created. The query could be extended with various types of joins involving other tables, but for now, I will only include a sorting expression that will arrange the result dataset by category name. When the expression is complete, some action function should be called. For now, we simply use done, which returns a reference to the root node of the expression. We then assign this reference to the variable called exp. By utilizing this reference, we can convert the expression into SQL code and output it to the console. In this particular case, I used T-SQL, but it could also apply to MySQL or PostgreSQL. Now we are ready to run our console application, expecting to see the actual SQL code. And yes, we can definitely see it. The SqExpress library comes with a straightforward wrapper around ADO.NET. Let's explore using it to retrieve data from an actual database. The first step is adding a reference to SQL Client Library that knows how to work with MS SQL Server. Once the library is available, we can create a database object that manages the SQL connection and passes the generated SQL code to SQL commands. To initialize the database object, I need to provide an instance of SQL connection with a specified connection string, a factory that creates a SQL command using the connection instance with a query text, and desired SQL exporter, a profile that indicates what SQL dialect is used when a query expression is converted into text. By default it is T-SQL, but also can be MySQL or PostgreSQL. Using the database object, we can execute an actual query to retrieve a list of records, which we'll store in a variable called result. To achieve this, we should switch our final action function from done to asynchronous query list. The first argument represents our database object, while the second argument is a lambda function that generates a result object. This function obtains a reference to a wrapper around an SQL record, which can then be used for the corresponding properties of the table descriptor. In this specific scenario, the lambda function generates a value tuple with 3 fields: ID, name, and description. Each field obtains its value and type from the read method of the corresponding column descriptor in the table descriptor. While it's possible to avoid referencing the table descriptor directly, doing so would require specifying the column name as a string, which could potentially lead to runtime errors. Now we can stop displaying the SQL query code and iterate through the list of value tuples that we will asynchronously receive from the database. Each tuple will be printed on a separate line, and since value tuples have a default implementation of the toString method, we can simply pass them to writeLine. Now it's time to run the application and ensure that the list of categories is displayed in the console. After ensuring this, we can proceed to join the categories table with the products table. This will allow us to view a list of products along with their corresponding categories. First, we need to instantiate an object of the table descriptor class that represents the products table. Next, the object can be passed into the left join function, which receives a link to a data source and a predicate. This predicate will be used to match records from the specified data source with other data sources used in the query. In this case, the predicate is a simple equation between the category ID columns of both tables. SqExpress heavily relies on operator overloading, and this comparison produces an abstract syntax tree node rather than a Boolean value. Next, we'll modify the lambda function that creates a value tuple. The purpose of this adjustment is to include the product name, which we'll retrieve from the recently joined table. Let's utilize the object representing the products table descriptor and specify the product name property, which corresponds to the relevant table column. Of course, the column should also be added to the list of values selected by the entire query. Otherwise, we would encounter a runtime error. Once again, we're ready to run our console application and verify that we retrieve a list of products from the database, along with their corresponding categories. Now it's time to perform a small refactoring. The essence of this refactoring is to extract the query we just created into a separate method that we can run later. Let's give it a straightforward name, like GetList. It will be an asynchronous function that performs the query and print it to the console. The function retrieves a link to a database object, which in turn establishes a connection to a database. Let's make it static to reduce the chances of undesired side effects. Previously, we only read some existing data, and now it's time to modify the data by inserting new rows into the products table. We can achieve this using the Insert into Fluent API, which is initiated by the corresponding method in SqQueryBuilder. As before, we require a reference to the table descriptor. Using this reference, we can specify a list of table columns affected by the insert statement. In this case, it will include category name and category description. Values for the insert statement can be specified similarly to how we do it in actual SQL code, by listing literals or other value expressions separated by commas. Let's add two new categories, eggs and milk, along with their corresponding descriptions. Similar to actual SQL code, we can add multiple tuples, but to complete the API, we need to call the DoneWithValues method. When the dataset is ready, we can invoke the exec method, which receives the database object and executes the insert statement against the specified database. The method is asynchronous, so do not forget to add the await keyword. Now let's run the console application and verify that the insert statement was executed correctly. We can observe that the two new categories were successfully added to the table. Let's try launching it one more time and see what happens. As the insert statement remains unchanged, it is hardly surprising that the two new categories were added once again, resulting in duplicates. However, from a database perspective, it appears correct since the identifier column is auto-incremental. Nevertheless, the situation allows us to demonstrate how data can be removed from the database. Let's use the Delete Fluent API and provide the target table category, along with the row predicate, which, using the in operator, will identify all categories whose name is eggs or milk. After completing this step, we will use the familiar exec method to execute the statement against our database. After making some minor adjustments, it's time to relaunch the application. After the console application finishes its work, we can verify that all the categories we inserted previously have been successfully removed from the category table. Let's attempt to insert the new categories once more, but this time we'll take a different approach. Instead of explicitly defining the data we want to insert into the database, we'll use a list of regular .NET objects as our data source. We will create an array of value tuples that contain name and description members initialized with familiar values. For demonstration purposes, the collection values are hard-coded, but in reality, it can be a collection of any length with any values that adhere to database restrictions. To insert a collection into a database table, we should use the InsertDataInto method. This method retrieves a target table descriptor, a collection of objects, and then initializes a Fluent API that maps object properties to table columns. The mapping is performed by implementing a Lambda function that receives a mapping interface as a parameter. This interface has a chained method called set, where the first argument is a column reference, and the second argument is an object property or any other suitable expression. The mapping interface also includes the target and source properties. During the execution of the Lambda function, these properties respectively refer to the target table descriptor and the next element in the past collection. By sequentially applying this Lambda function to all elements of the collection, the SqExpress library generates the set of values that will be injected into the insert statement. Here, we've created a straightforward mapping of the name and descriptor properties to the corresponding columns of the categories table. Before executing this statement, we will incorporate a simple trick to prevent duplicates from appearing in the database table. This is the checkExistence by function. It adds an additional predicate to the insert statement, ensuring that a value provided in a row does not already exist in the database. We've just run the application, and now we can see that the new categories have been added. Let's run the application one more time to verify that the incorporated trick works as expected, and we no longer encounter duplicates in the table. It seems it works correctly, and we no longer see the duplicates. Let's eliminate the insertion logic and revert to the function that solely retrieves information from the database. Now it's time to explore another significant functional area provided by the library, specifically, the degeneration of DTO classes for database tables. Within a table descriptor class, we can define a special attribute called SqModel for a property that represents a table column. As the attribute argument, we need to specify a DTO model name in which the property will be included. Now we can apply the same attribute to other properties that we want to include in the DTO model. As a result, the model will include properties for category name and category description. We can also generate DTOs with a different model name for the other tables. For instance, we are instructing the library to create a model named product with a single property called product name. To enable code generation, we need to add a specific property called SqModelGenEnable to the project file and set it to true. After that, the code generation will occur each time the project is rebuilt, allowing us to see the DTOs, which are by default placed into the models folder. Here, we can observe the two generated classes whose names we specified as attribute arguments and properties that were marked with the attribute. In addition to that, we can observe that the library generated a read method that performs mapping from a database record. Let's use the generated DTOs in a query. Instead of explicitly defining columns, we can utilize the getColumnStatic method of the generated model. As an argument, it receives a table descriptor instance to utilize its unique alias, as a single table may appear multiple times in a query. Now, using the appropriate table descriptor, let's add columns from the second model. Inside the Lambda function that creates an element of the resulting collection, we can use the auto-generated method read that was mentioned earlier. The first argument represents a wrapper around a database record, and the second one is the table descriptor that contains table column names. We will also utilize the static method read from the relevant model for the products table, specifying its table descriptor. However, in the case of the products table, we need to consider that it is joined through a left join, which means that the record might be null. Therefore, we need to include an explicit check where we can use another automatically generated method called isNull. This method returns true when none of the mapped columns in the record have values, and if this occurs, the entire model should be null. After replacing primitive properties with DTO models in the elements of the resulting collection, we also need to update the console output to reference the auto-generated properties of the corresponding models, the category name and the product that belong to the category. Given that the product might be null, we need to include additional logic here and establish a default value for cases when a category has no associated product. And now we can execute the console application and verify that the mapping performed using auto-generated models is correct. Let's make a slight modification to our query and add a filter by category, ensuring that only products belonging to the beverages category are visible. To achieve this within the Fluent API call chain, we need to add a where function that accepts the corresponding Boolean expression. Once again, the C# operator overload is utilized here. Running the application again, we can see that the filtering works correctly. By adding the offsetFetch function to the chain, you can retrieve a specific range within the result collection. In this video, we briefly explored the fundamental functionality of the SqExpress library. It enables you to execute significantly more complex queries and perform various tasks. For additional details, refer to the README file on the project's GitHub page. Thank you for watching.